In this example, we are supposed to find the difference between the functions f of x and g of x. Difference is a math word for subtraction, so what it's asking us to do is find f minus g of x. So in order to do this, we literally take the f of x equation, which is 3x plus 4, and we subtract the g of x equation, which is x squared minus 5x plus 2. It is very important that we place parentheses around the expressions whenever we're setting up the operations. After doing so, we just simplify like normal. Since there's a minus sign in between the two sets of parentheses, we need to distribute it through. So we'll end up with 3x plus 4 minus x squared plus 5x, and then minus 2. And after doing so, we're going to combine like terms. I prefer to write it in standard form, so that's what I'm going to do here. So my highest power is x squared. So negative x squared comes down. Then we have 3x and 5x to make 8x. And then lastly, 4 minus 2 is 2. So this is the result, or the difference between f and g. In this example, we have two functions, f and g, once again. We're going to write the expression for the product of f and g. Well, product is a word meaning multiplication, so we are asked to find f times g this time. And just note that this is a closed dot for multiplication. That becomes important when we talk about composition later. Now, f of x is the equation or expression 2x plus 3, and again putting in parentheses. And then g of x is the expression x squared plus 5. This time I don't have to put an operation in between them, because if there's no operation between two sets of parentheses, it's implied to be multiplication. But like before, we still need the parentheses. After setting it up, I just have to distribute it out. So 2x times x squared, we have 2x to the third. 2x times 5 is 10x. 3 times x squared is 3x squared. And 3 times 5 is 15. It is helpful if you write in standard form as you combine like terms. We don't actually have any like terms on this expression, so just writing in standard form is nice. So in standard form, we have 2x to the third plus 3x squared plus 10x and plus 15. In this example, we're finding the quotient of f over g for the functions f of x equals 2x minus 14 and g of x being x squared minus 2x minus 35. To start this off, we're going to start it off the same way, setting up the expression f over g. F of x is 2x minus 14 over g of x, which is x squared minus 2x minus 35. You'll notice this time I didn't write parentheses, and that's because with the fraction bar, parentheses are automatically implied to be around the top, and same thing for the denominator. Now we have to do the simplify part. So for simplifying a fraction, we need to look at the common factors and cancel them out. So we're going to have to factor the top and bottom. The top, we can just pull a common monomial of 2 out of both terms, giving us x minus 7. And on the bottom, there's no common monomial, so I'll go through and factor as a trinomial. The combination that multiplies to be negative 35 but adds up to be negative 2 is 5 and negative 7. And since there's no leading coefficient, we can jump straight to the factors of x plus 5 and x minus 7. The common factors cancel after factoring the top and bottom. We have a common factor of x minus 7, so that will cancel. And the simplified expression, therefore, is 2 over x plus 5. However, with division, we're not quite done after factoring. We still need to state the restrictions because there is now a bottom of the fraction, and the bottom of the fraction can never be 0. We also have to tag on x can't be, well, whatever values would make the original bottom 0. So we look at the original bottom and set it equal to 0 and solve. And we're going to use the factored version because one of the ways of solving a quadratic is by factoring. So we're going to take each factor and set each factor individually equal to 0. After doing so, just solve them. So we have subtracting 5, we get x equals -5, and adding 7, x equals 7. So the two restrictions are -5 and +7. So overall, we have the simplified expression and the restrictions on the domain for this combined function. Now, next, we're going to be looking at function composition. Function composition is where we basically take one function and place it inside of the other. So if we have the functions f and g, f composed with g, and notice right here is an open dot, not a closed dot. Closed dot refers to multiplication. The open dot refers to composition. So f composed with g, and it's defined by f of g of x. So we're taking the g of x equation and plugging in to f. Now that's actually nothing new because we have done that before, just our equations were just numbers. So like if we plug f of x, if f of x is our equation, and we have f of 3 is what we're looking for, we're just replacing x with 3. The same idea will apply here. It's just now expressions. And you may have also done something like this where you're plugging in a plus 3 into the equation to give you 5 times a plus 3 minus 1. So we're just extending stuff you've likely already done to doing it with two different functions, possibly different types of functions, and combining it into one expression. Now the next notes are about the domain and range. So the domain of the composed function of f of g is the set of all domain values of g whose y values or range values are in the domain of f. And the reason being for this is you can't plug anything into f if it doesn't work. For example, if f of x is a fraction, you cannot plug 0 into the bottom of a fraction. So if 0 was in the range values or the outputs of g, we would not be able to use that as part of the overall function. So whichever x values would trigger the y value of g to be 0, we would have to eliminate that from the possible domain values of this composed function. And then right below is just a simple example of a composite function where we have a linear and a square root function composed together to give us the square root of 2x plus 1. Okay, so we're going to be looking at a composite function here. We have the composition of f with g. Now, I like to, whenever I first start doing this, color code them. I find it nice to help get started with this. So I'm just going to code my f of x equation in green and my g of x in blue. So as I start setting it up, the f composed with g, what that means is f of x will be on the outside. We are plugging in to f of x our g of x equation. Whenever I first start teaching this, I always recommend the approach to use is just go through your outside one, and anywhere you see an x, replace it with a blank set of parentheses. So f of x is 2x minus 1, so I'm going to write 2 blank set of parentheses minus 1. Give myself enough space inside the parentheses to write something. Now what goes inside the parentheses? Well, g of x does. G of x is what I'm plugging into the f of x equation. And g of x is x plus 1, the sum of x and 1 over 2. So we're going to put x plus 1 all divided by 2 in the parentheses. Now it's just a matter of simplifying this, and from here on I'm not going to too much worry about the color coding that I used for setting it up. but I have a fraction times 2. 2 as a fraction is 2 over 1, and we have a 2 on top, 2 on the bottom. They'll cancel out, leaving us with x plus 1, and our minus 1 on the outside of parentheses dropping down. Then combine like terms, 1's cancel out, and we get x. Now x is very special when you're doing composition, which we'll look at later, but if you get x in this for both f of x or f of g and g of f of x, then these two have a special relationship where they are called inverses. In other words, they cancel each other out, returning it to the original value that you plugged in. And composition is one of the ways of finding or proving if two functions are inverses. And this special function x, or y equals x, is the identity function. Which is important to distinguish because like any inverses, for like the additive inverse, so 5, the additive inverse of 5 is negative 5. It gives you the identity for addition. And there's also similar for multiplication, where the identity of multiplication is 1. So the fact that this creates the identity function is very important. But of course, these two functions are only inverses if both f of g and g of f are both x. But that's kind of a tangent for another time. Okay, so here we have another composition of f with g. We have f of x being x squared plus 2x plus 2, and g of x being 4 minus x. So f of x is once again the outside function. I'm going to color code that in blue, while the green will be for g of x. F of x comes first in the f open dot g, so f parentheses, and g is going to be plugged inside. So as I actually set up the expression that I'll have to simplify, I'm going to go through the outside function, which is the f function, and anywhere I see an x, I'm going to put a set of parentheses. I see two x's here, so I'm going to be putting two sets of blank parentheses. So we're going to have, instead of x squared, we're going to have parentheses squared, plus 2 times x, or 2 times parentheses, plus 2. And now I'm going to go back through and fill in what g of x is. G of x is 4 minus x. 4 minus x. Now that it's set up, we can go ahead and simplify. As a reminder, if this first term had a multiplication in front of it, you would first have to deal with the exponents, because when you simplify, you follow order of operations, so exponents come first. That's not the case, but either way, we still have to handle the exponents first. So you can either use the property to distribute this out, or you can write 4 minus x out twice and distribute it out that way. Whether you use the identity to distribute it or you distribute it out like normal, you should still get 16 minus 8x plus x squared. Since the second term here is connected by addition and subtraction, we can go ahead and distribute that. We won't violate any order of operations if we do that, so we're going to distribute the 2 through, giving us 8 minus 2x. And then that last little plus 2 has no multiplication or exponents involved, so it's just going to drop down. And now we have no other multiplication that's doable, so we will just combine like terms. So our highest power is x squared. Then our x's, so we have negative 8 minus 2 is negative 10x. And then we have just our coefficients, so 16 plus 8 is 24, plus another 2 is 26. And you can see on like this, the first one, this one came out to be something different and not the identity function, which is fine. This happens more often than the identity function comes about. Okay, in this example, we have a composition of f with g. So we have two functions, f of x, which I'm going to use blue for, and then g of x, which I'm going to use green for. This is a little bit different because one of our functions is no longer a polynomial, it's a square root function. So if we start up by setting up the composition, so f comes first, because it's first in the initial expression, and then we have g coming second, so g is going to be plugged inside of the f function. So we're going to go through the outer function, which is f, and replace x with parentheses. So here is f, and we only have one x in there, so we're going to replace that with parentheses. So 2 parentheses squared plus 5. And then I'm going to go back through that and replace the x and fill in my parentheses with the square root of x minus 2. Now that I have it set up, I just have to follow order of operations to simplify. I can't do anything with the stuff inside the actual parentheses or inside the radical. However, exponents come next, and we can deal with having a square and a square root. They'll cancel each other out. Because there is two terms, however, I still need to maintain the parentheses. So we'll have 2 times in parentheses x minus 2 with the plus 5 coming down. 2 is connected by multiplication, so we'll distribute it through, giving me 2x minus 4. And then combine like terms, giving us 2x plus 1. And there we go. We should also consider domain and range. So a polynomial function does not have any restrictions on domain. It's the outer function, so we would have to consider it if it was the inner function as far as what outputs would need to be considered for the domain and range, but it's the outer function, so we really want to focus on this inner function here. We don't have to worry about any restrictions on the domain of f. But with the domain of g can only be, or square root functions can only be numbers where x is greater than or equal to 0, which, because of the transformations, because of the minus 3 inside x opposite, means we're going to add 3 to that, turning x greater than or equal to 0 into x greater than or equal to 3. So that would be the restrictions on the domain of this composite function, due to not being able to input all x values into the original g of x. Okay, so there are two methods to do the evaluation here. Now, what the evaluation will look like is it will have the expression or operation we're supposed to do, followed by a set of parentheses, and normally there's an x there if they choose to write that operation. However, if there's a number there, that means we're going to plug that number in. It does not mean distribution. That's one of the common mistakes, is people try to take this number and distribute it through the rest of the expression. It is not distribution, it is evaluating. So we're going to evaluate the expression f minus g with the x value of -2. Now there's two different ways to do it. One way is to first calculate the operation and then evaluate, and the other way is to evaluate and then calculate the operations on the functions, or do that as you're doing the operations. But we're going to start with this one where we calculate the operations first. So f minus g, so we're going to take f of x, which is 3x minus 7, and then we're going to take g of x, which is x squared plus 5x plus 6. They're connected by subtraction. So we have to simplify this expression. We're going to calculate the operation first, distribute through, giving us 3x minus 7 minus x squared minus 5x minus 6. And if I combine like terms, we're going to have negative x squared. We got positive 3 and negative 5 to make negative 2x. And then negative 7 and negative 6 to make negative 13. However, we are not done there. We're also asked to evaluate it with -2 in for x. So I'm going to go back and do the evaluating part now. I'm going to replace x with -2. So negative -2 squared minus 2 times -2 minus 13. If I go through and simplify it, we have positive 4, but when the negative comes down, it will be negative. We've got double negative multiplied together to give me positive 4 minus 13. Positive 4's will cancel out, leaving me with negative 13 for the overall evaluation of the expression. Now, while there's two methods to doing this, depending on the exact situation, one method may be more beneficial to the other. For example, if you already have to calculate the operation, or if you're going to be doing the same operation and plugging multiple different numbers into it, then this way may be better. But if you're only going to be evaluating once and not actually having to do the operations in the first place, then the other method is probably more handy. It's also more versatile because it can be used with tables as well as graphs. So in this example, we're going to be looking at composition where we calculate the operations first. We're doing a basic example or basic operation one and a composition one because composition behaves a little bit differently. But to calculate the operation first, we're going to first start off by doing f of g of x. And then after finding that, we'll deal with what we're supposed to plug in to evaluate. My f of x equation is 3x minus 7. So I'm going to put 3 parentheses minus 7. And then inside the parentheses, I'm going to put my g of x, which is x squared. I may not have left enough room. Plus 5x plus 6. Cool, got it. Just enough room. Now we're going to distribute it out. So distribute my 3 through. Give me 3x squared plus 15x plus 18. My minus 7 is coming down. And if I combine like terms, I have 3x squared plus 15x plus 11. Now we still have to do the evaluating part. We need to evaluate by plugging in -2 because that's what we have after our composition setup. So we'll replace x with -2, giving us 3 times -2 squared plus 15 times -2 plus 11. And if I simplify this, starting with exponents, we have -2 squared, which is positive 4, and 3 times 4 is 12. 15 times -2 is -30, plus the 11 dropping down. What I do know as a quick way of doing it in my head, I have 12 and 11 to make 23, and 23 minus 30 is -7. So all in all, it should evaluate to be -7. Now, I mentioned that there are two different methods. In a second, we're going to do the other method. However, there are just slight variations with doing this. Like as I set this up, I could have also plugged in what I was trying to evaluate here as well. So there's many other variations on these two broader methods I'm going over. Okay, in this example, we're going to be doing kind of the same thing, the evaluation, but this time we're going to be doing it in a different approach. So the second method is where we're going to evaluate the parts separately, and then we're going to put it together with the operation. So another way of saying f times g of 3, the definition of what it means is f of 3 times g of 3. We can easily find those two values separately. If I find f of 3 off to the side here, f of 3 is going to be 2 times 3 plus 3. 2 times 3 is 6, and 6 plus 3 is 9. So I know that f of 3 is 9. I can now find g of 3 with my g of x equation, which is x minus 5, so 3 minus 5, and 3 minus 5 is -2. So I now know g of 3 is -2, so I'll replace it with -2. These two are connected by multiplication, so we are going to multiply 9 and -2 to get -18. So if you're only doing the evaluation part, doing this method or this approach is usually a lot quicker if you're only doing it once. If you're doing it several times, it may be quicker to do the other way. It just depends on your comfort and how big the expressions and numbers are. Okay, so for this, composition can look a little bit different, so we're going to do a composition example as well. So this is f of g of -3. So if I go through and set it up, we have the outer function, which comes first, f of g. But this time, instead of putting x there like we've been, we're going to actually evaluate it at the same time, putting my -3 in there. And now we're going to evaluate it in parts. So we're going to deal with g of -3 first. Well, g of -3 tells us to go to the g equation and replace x with -3. So -3 minus 5, which is, that's a horrible 5, which is -8. So I know that g of -3 is -8. So I can replace the entirety of g of -3 with just that. So what was once f of g of -3 is now f of -8. Now hopping over to the side one more time, I can easily find what f of -8 is just by replacing x with -8. So 2 times -8 plus our 3. 2 times -8 is -16. Plus our 3 is -13. So now that I've done that, I know that f of -8 is -13, leaving us with the fact that f of g of -3 is equal to -13. Okay, in this example, we're going to be looking at the functions f and g, but we have them graphically instead of their equation versions, which means we're not going to be able to use the first method listed earlier because we don't have the equations to calculate the operations for us. So instead, we are going to have to use that second method, but that works out great. If we want to find f of g of 1, that's fairly simple. We have f of g of 1. So I'll color code there. So first, we start with the innermost operation that's happening, the innermost evaluation, the g of 1. Well, g of 1 would mean we're going to go to the g of x graph. We're going to find the x value of 1, which is right there. And then we're going to go up until I find my graph, up or down until you find the graph. What's the y value there? Well, the y value is 2. So I know that g of 1 is 2, meaning we now are looking for f of 2. Since we're looking for f of 2, I'm going to go to the f graph now. I'm going to find the x value of 2, which is right here. And then I'm going to go up or down until I find my graph. I have to go all the way up here, not a very straight line. And then for the y value, which is the result of f of 2, we get 4. So the answer for f of g of 1 is 4. And if this was one of the basic operations like addition, you would just calculate the two functions separately and then add them together if it was addition, or multiply them if it was multiplication, and so on. In this example, we are given a table and we're asked to find two different operations using this table of values. So this table contains x values, then we have values for f of x, the y values for f of x, and the y values for g of x. For part A, we're doing a basic operation. We are doing the operation f plus g of 3. And since we can't use method 1, since there's no equations, we're going to use method 2 by separating it, looking at what f of 3 is, and what g of 3 is, and then adding them together. Well, we use the table to find these values. F of 3, according to the table, here is the x value of 3. If I go over to my f of x column, we get 5. And then for g of 3, well, again, here's the x value of 3. We're going to go over to find where g is 3. Well, the y value when g is 3 is -4, and if we add them together, we get 1. So the answer for part A is 1. We have a part B here, so part B is going to be kind of the same deal. For part B, since it's composition, we're going to have f of g of -2 here. Well, we're going to start by dealing with the inside. We're going to look at g of -2. Well, -2 on the x-axis, or x value, is right here. The g value, or the y value for the g equation, when x is -2, is 5. So we have f of 5. And then from there, we need to find the x value of 5 on the table. So the x value of 5 is all the way down here. And then we need to look at the y value for the f column for the function f, which is 7. So overall, part B evaluates into 7.